Hello, it's Keith here, and this is lesson 3 of the platform-specific series of my Z80 tutorials. Now we're going to start a set of 3 tutorials. We're going to learn how to get data onto our screen, bitmap data, and we're going to do this in ways that kind of work in a similar way or in the exact same way on all 3 of the systems, irrespective of the underlying hardware layout. So this is going to allow us to show bitmap data and also font data in a common way, and we're not going to use the firmware at all, so we're going to be doing this entirely ourselves by accessing whatever video hardware the system has. Now, of course, we're going to be covering 6 systems in total. We're going to be covering the Amstrad CPC, the Enterprise, the MSX, the TI 83 calculator, the Spectrum and the SAM Coupe, and they have very different hardware. So because of that, I'm going to split this into a set of 3, and we're going to cover 2 platforms per episode. But I would ask you to please watch all of the episodes, even if you're not particularly interested in that system, because as I say, the function calls will be common to all of them. And even if you're not really that interested in a particular piece of hardware, there is plenty to learn there about how we're manipulating data, how we're accessing that hardware. And so I think if you really want to have a good, well-rounded knowledge of the Z80 platforms, knowing the systems that you're not necessarily interested in programming will give you more experience there, and it's definitely worth doing if you do have the time. So anyway, today we're going to cover the Amstrad CPC and the Enterprise. These 2 systems have very similar graphical hardware. The Enterprise can basically emulate an Amstrad CPC, so there'll be very little difference between the 2, and that's why I've done this one first, because it will give us some time to have a look at the general setup I'm using, and then we can look at the Enterprise and the Amstrad CPC. Okay, so what are we going to do? Well, we're going to create 2 functions for our use, apart from the screen setup routine, that is. The first one will put platform-specific bitmaps onto the screen. What this means is if we have data that's structured in the correct way for the color organization of the pixels in byte format, shall we say, we can put the data straight to the screen. So we would need to make sure our bytes are in the correct format for the system screen, but this will give us a quick way of getting data from a bitmap file onto the screen. Today we won't have a bitmap file, we'll just be showing consecutive data. We're going to start by filling with 255, and then we'll go 254, etc., all the way down to 0, and we'll print those into a square, which you can already see in the corner of the screen here. So that square will represent what the byte data looks like on the screen, and as that will be specific to the hardware. Now the second thing we've got is platform independent, and what that is it's going to take a byte that is in black and white format, so a 1-bit bitmap, and it will show it onto the screen in a 2-color format. So with the Amstrad CPC, it's 2 bits per pixel, but we've used our 1-bit data, and the code we're going to look at today will convert it. So you can see the letter A font here is actually been created by this bitmap data here. Well, what's the main use of this? Well, in the case if we are wanting to use a common black and white data file, we can actually show that on every single system we're going to learn without any conversion, because the ZX Spectrum with its 2-color, its black and white system, and the SAM Coupe with its 16-color system will obviously need very different bitmap data to fully use those systems. But we may want to have a font file that's common to all the systems and be able to show letters on screen in a common way. And so we're going to create this 2-color command called setScreenByte black and white, which will allow us to kind of bypass all of that complexity and just use very simple data. So anyway, enough of the introduction. Let's actually have a quick look at the code, the common code we're going to create, which we will be using much more advanced ways later. But today I'm just going to introduce it so you understand when we look at the underlying structures what they are actually looking to achieve. So we're using our standard do init command here, which will just initialize the system itself. But then we've got this new screen init command, and what this does is it initializes the hardware in whatever way the system requires. Of course, that will vary wildly depending on the system we're using. We'll look more at that later. Now, next we've got a command called GetScreenPause, and we are passing that an XY coordinate. The X is in bytes, so on the Amstrad CPC it's 80 bytes wide, and the Y is in lines, and the CPC is 200 lines tall. So you might think that's a little bit odd. Well, working on these systems in pixels is very difficult, and it's also very slow because it's very difficult. So you will tend to work in bytes in most cases, and so while it does remove the system independent nature, it makes it much more platform dependent. It is kind of a requirement of simple coding, and later on we're going to look at my sprite converter, which will allow you to import bitmaps and then export them in the format required for the systems. So I think this is the better way of doing things, working in bytes rather than trying to convert data on the fly on the slow Z80. Instead, let's make C#, my sprite editor, do the conversion work for us and give the different systems different files. So this is the GetScreenPause command. We're then setting B to 255. We're using a macro for the first time here called setScreenByte. We'll look at the macro later. A macro is a kind of text template which the assembler actually replaces with bytecode. So it's not handled by the Z80. It's kind of automatically replaced. We'll see more later. But we're using this macro setScreenByte with the variable with the register B. We then decrease B. We are then doing this little command here to check when we need to do a new line, just to make it, rather than one big line, we wanted a square, so it will fit on our small screen of the TI-83 basically. And then if we need to, we start a new line. We check if B has reached 0 yet, and if we haven't, we repeat. Once we've done that, we move our cursor again to the new position where we're going to show our sample font. We've only got one letter today, but all we do is we set DE to the position of the letter. This is because HL is used by the the screen functionality as the current cursor position on systems like the Amstrad CPC. So we're using DE in this case. So then we set DE to the letter, and if you remember, we had a look at the letter earlier. Here it is. So all we're doing is we're reading in a byte from DE. Now these are represented in bits, so this is 1 byte here, and you can see 1 byte is the entire width of one character here. So we've got 8 lines in total. So all we're doing is we're setting the byte 3 times, and that's because we're showing 3 A's just as a test. It automatically moves across the screen every time we put data to the screen, so that's why you can't see any command doing that. Now then we move down to the next line, and we keep repeating until we get to the blank line. So this is actually assuming that the bottom line of the font will be zeros, which may be incorrect. We may want to actually assume that there are 8 lines, or we may want to have a specific byte pattern that means you've reached the end. But as I say, in this case, just a very simple example. We're going to take it far further once we've covered these basics on all of the systems. So that's what we do there. We've got a function called bitmap memory here, which is got all of our platform specific code nested in it. We'll have a look at that platform specific code later, but I just want to show you some of the functionality that I'm providing specifically for the Enterprise and the Amstrad CPC. Now the Enterprise and the Amstrad CPC are a bit unusual because whereas systems like the TI has very limited options, it's only black and white, not really many choices there. The Spectrum has no real screen mode options. It's always 256 by 192. It's always 2 color with color blocks. But on the Amstrad CPC, we do have some quite interesting choices. Firstly, the screen is an odd size. It's 320 by 200, which is great for screen space. But if you're trying to write one game on all of the systems, you may actually prefer if the Amstrad CPC had the same screen size as say, the ZX Spectrum, 256 by 192. And we can do that. All we do here, if we unrem this line here, and we'll just reset our emulator here. I should actually just show you. Well, just before I do that, let's just prove that this does work on the Enterprise as well. I have not shown that yet, so we'll just unrem Enterprise. So we've just compiled that here. And if we run enter disk here, you can see now the exact same sort of thing here. Now the colors are different up here, and that's because, as I said, this is a platform-specific bitmap. So depending on the system, the appearance will be quite different. But we're going to get around that later, and you can see the font below. Now on the Enterprise and the Amstrad CPC both, we can choose to limit our screen width to the equivalent of the ZX Spectrum and the SAM Coupe and the Enterprise, 256 pixels wide. And this code will do that automatically for you, so you can see now the border's a bit wider. If you prefer, you don't want to use 4-color mode, well, we can do that too. We can do both as well. We'll just compile that. And there we go, we're now in 16 color mode. But you'll see, even though the bitmap at the top is now in 16 colors, you'll notice that the font at the bottom, while it's got wider because the screen mode is half the resolution, it is still represented perfectly because that 2-bit bitmap has been converted into what is appropriate for the screen. So there we go. Now let's make a start and let's have a look at what is actually doing all of the work here. So we'll start with the Amstrad CPC and we'll start with the initialization routine. So the first thing we need to do is if we're not using 16 color mode, we want screen mode 1. If we are, then we want screen mode 0. Now by default I've provided a firmware function here that will set the screen mode. That's okay to use, but generally here we are showing ways that will work even if you don't use the firmware at all. Now you could argue that that's okay, but maybe you don't want to use the firmware even for that single function. Well, that's fine. There is another way of doing it. What you do is you just send 7F in B and then 128 plus either 1 or 0 in C, and you just out that to the gate array and the screen mode will change. However, there is a rather interesting limitation of this. The firmware interrupt handler, whenever it kicks in, will reset the screen mode back to the default. Now you probably don't want that to happen, so you've got two choices: completely replace the firmware interrupt handler or disable interrupts, or alternatively you can work with the firmware interrupt handler. The firmware interrupt handler requires the shadow register BC to equal a specific value, and we can actually set it to that correct value here and then switch that into the shadow registers, and that will keep the firmware happy and stop it from changing the mode back. But as I say, you're perfectly welcome to use that. I tend to use the firmware one because I do this at the start of my game, and then after that I never do it again. And so by using the firmware one, I don't need to worry about the firmware going a bit crazy on me and messing things up. But as I say, don't want to use the firmware, or you've broken the firmware, well, you can do that alternate version. And now, if we're just going to use our normal 320 pixel wide mode, then we've got no more to do. But if we are going to use 256 pixel wide mode, we have to reconfigure the system. Now the Amstrad CPC has a chip called the CRTC, and this handles all of the screen display with regards to the cathode ray tube. There's a lot of different options, as you can see here, and they're very, very advanced, and you can do some really clever things with them that are far more clever than I can explain to you. But if you just want to make the screen mimic a ZX Spectrum, then these are the values you use. The CRTC has 14 registers and numbered 0 to 13, and these are the values you need to use to set it up as a Spectrum, or similar to a Spectrum, sorry. So we're just pushing these out to each of the registers, and then once we're done, we just return back. So that's the setup routine that you saw at the top of just this here. So let's move on now and let's have a look at the GetScreenPause function, and you'll see there's two versions of this, just depending on if we're using a screen width of 256 or not, but they're both basically the same. So the GetScreenPause function is quite simple. We've covered this before in the basic series, I believe, but all it does is it gets the address of the screen table, and then it selects a line based on the current Y position, the requested Y position. It adds it twice to the HL because each Y position has 2 bytes in the address. The screen base is at C000, but we need to add our X position in bytes as well. So we set B to this and C to the X position, and then we add that to the loaded in memory position of the line from this line table, and then we have the complete position. We're making a backup because our GetNextLine function will want to know the original line, because we're using it as a kind of grid to draw a square area. So what we do is we fill along and then we move back to the original position, kind of like a carriage return command. And so by storing the last GetScreenPause function position, we know where to reset to when we do the GetNextLine command. So that's a kind of simplifier that we've used here. Now the screen table we are using will vary depending on the screen size, but the function other than that is the same. Now GetNextLine, as I have mentioned in a previous lesson, on the Amstrad CPC the lines in pixel locations aren't directly beneath each other, and you can see this by the fact that these numbers are changing wildly here. And so what you do is you add 800 to a memory position, and that should get you the next line below, but every 8 lines you'll go off the bottom of the screen, and so you need to check if in this configuration if bit 7 has flipped to 0, and if it has, you need to add CO50 to get back to the to kind of flip you back to the correct position for the next screen line. But once you've done this, it's a bit complex, but you can just use it as is here. And once you've done that, you will actually have a correct screen position for the next line that was directly below the last one. And then all we do is we back it up again so that when we run the command again, we will get the next line below that. Now this is very slightly different if the screen is a different size. You'll see up here it's CO50, but if we're using a 256 pixel widescreen, it's CO40. But apart from that, this function is the same. Okay. So there we go. Now that's covered everything in this bitmap memory function, this bitmap memory file, but there is some more commands here in this bitmap header file. Now what this is this is where the macros are being stored. So these needed to appear in a separate place, and so we've just defined them separately. Now these we'll cover later in a later lesson because they're related to something else. So the first macro we're defining is the NextGreenbyte command here. And what does this do? Well, whenever we set a byte on the screen, we're moving along automatically to the next byte so that we can set that later. But there's a kind of saving we can do. If we're in 320 pixel wide mode, we have to ink HL, which takes 6 ticks. But if we're only in 256 pixel wide mode, we just need to ink L, and that takes 4. So we can get a small saving, and that's one of the good reasons for using 256 pixel wide mode. Not only is there less pixels to cover, but you can actually cover them faster. And on the Amstrad CPC, that can be quite important because the Amstrad CPC screen is already much bigger than the ZX Spectrum screen, which is part of the reason why the games are often slower. So it's bigger in bytes because it's 2 bits per pixel, not 1. But then when the screen size is bigger as well, that makes it even worse. So this is a sort of way that you can get a bit of a saving on the Amstrad CPC, speed saving. So that's something that's definitely worth considering. Now when we do set screen byte on the Amstrad CPC, it's very easy. All we do is load HL with the byte that we wanted to use. Now you'll see that there's a definition new byte here in this macro definition, and that will be replaced with a register. And so if you do set screen byte B, which is what we did earlier, then this new byte here will be replaced with B. If you don't understand macros, I'm not going to go into them in too much detail here. Please have a look at the help files in WinApe because they are explained in detail there, but really they're not that complex, and you don't really need to worry about them too much because you can probably kind of understand what they're doing on screen here, and if you don't really need to make any changes to them. So now the next command is a bit more tricky because we're using this set screen byte black and white. Now this is the one that will take in a value from the accumulator, and it will convert it according to the screen mode so that we can plot our 2-color font onto the screen in the same way, irrespective of screen mode. Now in 4-color mode, that's pretty simple. All we do is we take the first nibble and then we plot it to the screen. We move along, we take the second nibble, we shift it to the same position because we want it to be the same color, and we plot it to the screen again. Now if you're not sure about this, I have covered the Amstrad CPC screen mode before, but I'd suggest what you do is you try plotting some various bytes with the peek command. If you do it with the poke command, if you do poke and C000, comma, for example, and FO, you'll see some data was poked there. And then if you change it to OF, you'll see it changed color. And that's why we're shifting these nibbles around to keep the half the same color. But as I say, if you're not sure, please play around with either assembly language or basic and poke some data to the screen until you understand what's actually going on. So the 4-color mode is pretty easy, but the 16-color mode is a bit more of a pain. Because now there's only 2 pixels per byte, we're having to move across 4 times, and we're having to slice the 2-bit bitmap into 4 chunks and do lots more shifts to get it to work. But the effect is still the same. We're now covering 4 bytes with 4 different chunks of 2 bits each. But when we get to the end, the result is the same. You can see here as well, we're having to do a lot of push pops to protect all of the registers so that we're not corrupting anything. But the end result of all of this is that you can show a 2-bit bitmap on either the 16-color or the 4-color mode in the same way. So that's the Amstrad CPC. Well, what changes on the Enterprise? Well, actually surprisingly little. Let's have a look. So first you can see the NextGreenbyte command is identical. We're still shifting HL and just L here, and that's because the screen, horizontally, the screen is exactly the same. Now the set byte command, the set screen byte command is identical. We're just pushing the data straight to the screen, and the screen layout is exactly the same on the Enterprise in 4-color and 16-color mode to the Amstrad CPC. So if you understand the CPC, you understand the Enterprise, great. But anyway, let's move on. So again, the 4-color bitmap font function is identical here, and so is the 16-color one. So we're not going to look into any detail in there because they are absolutely identical. But when we get to this bitmap memory function, there are some differences. Well, let's have a look. So we've got our screen address table here, and the screen addresses are different. The reason for this is, while horizontally the Amstrad CPC and the Enterprise are identical, the Enterprise does not have that problem of having to add 800 per line. You actually add hexadecimal 50, which is 80 bytes. Each line is progressively directly below the previous one, so getting to the next line is actually much easier. But because of this, the definitions for the table are completely different. No, that's no problem at all. I'll just show you actually how I created these definitions. So here is LibreOffice, but you could do this in Excel if you prefer that. Now you can see at the top here I've got some calculated definitions here. And you'll see down here I've got some line numbers, and then what I'm doing is I'm using hex to dec here to create a byte position. Now the one I'm showing here is actually the Enterprise one, you'll see. So I've got the decimal value here, which is the distance in lines, and then here every 8 lines I'm calculating again here, and then what we're doing is we're converting these decimal values into hexadecimal, and we're adding a comma, and then I can then copy these into a notepad, add the def W's at the start, and I literally use this to kind of generate the code for me so that I didn't have to calculate and type in all these numbers. And as I've said before, the dec to hex, hex to dec, dec to octal, etc. There are loads of great functions within Excel or LibreOffice that will allow you to work out, not just work out hexadecimal values, but if in cases like this you need a table of references that are mathematically calculatable, then you can actually create the code for you and just copy paste it in, and that is exactly what I did on all of these systems. So it is something that's worth considering there. So yeah, this is the 320 pixel wide version, and here is the 256 pixel wide version. So the get position command's no different to the Amstrad one, but the GetNextLine command is much simpler. In this case, all we're doing is we're adding, in the 320 pixel wide version, all we're doing is we're adding hexadecimal 50, which is 80 bytes, because that's how wide the screen is. If we've not overflowed L, then we return, but if we have, then we increase H. We do it in 2 parts because adding it as a 16-bit number is slower, so we add it as an 8-bit number and then check if we have to increase H as well. So that's the 80-byte wide version. The other version is 64 bytes wide, and so what we do here is we add hexadecimal 40. But apart from that, it's exactly the same. It's almost exactly the same as the Amstrad version. It's just because it's actually simpler on the Enterprise, the code has been optimized a little bit more. Now, initializing the screen on the Enterprise is unfortunately quite tricky, as you can see here. So I'm going to go over this, so brace yourself please. Now, the Enterprise screen is much more advanced than the Amstrad CPC one. I said it worked in the same way as the Amstrad CPC, and it's true that it can. It can actually even work in exactly the same way, where the lines are 800 bytes separated in a kind of interlaced fashion, but by default it does not. And this is where the Enterprise really comes into its own. You see, the screen is actually reconfigurable in a very, very wide range of ways, and it's the hardware that handles the reconfiguration. On the Amstrad CPC, if you want to change colours halfway down the screen, you have to do it in software. The Enterprise can do it in hardware. The Amstrad CPC can change screen modes multiple times per screen, so can the Enterprise, but the Enterprise does it in hardware with no processing power used at all. And the way it does that is it has something called a line parameter table, which you can see an example of at the bottom, which defines everything from the pixel data, the organization and color depth of that pixel data, the colors used by that pixel data, and also the borders and the screen positions itself. And so what you've got here, I've kind of given some notes on it, but I'm not going to go into in too much detail today. But what you've got here is a definition that says, well, and each of these definitions is 16 bytes. So the first definition says, well, this is 200 lines. And then this definition here says either this is going to be a 16 color mode or a 4 color mode. And then after that, we define the edge borders. And by doing that, we're defining whether the line is 320 pixels wide or just 256. Going on beyond that, we have the screen memory definition, which is where the data appears in the first 64 kilobytes of the Enterprise's memory. And if you're not understanding this, I know this is complex, but so you can just ignore this and just use the code I've given you. But I wanted to try and explain it a little bit at this stage. So this is the memory location that was defined by the previous code, which we'll look at in a bit. Now, the next part defines the colors. There are actually only 8 colors that are defined, and the second set 8 colors in 16 color mode are actually the same as the first 8 with a brightness offset. So the second 8 might be the same but twice the brightness or something. So it's not quite as flexible in 16 color mode, but all of the same flexibility and actually better color options in the 4 color mode. But as I say, the first 8 colors are definable with an RGB palette setting. Each RGB is defined as a single byte, and there's actually a sort of a weighting. There's only 2 bits defining the blue color, but there's 3 bits defining the red and the green. We will look at how to define colors on all of these systems in a common way later, but at this point it's too premature because we've got enough complexity here. So that defines the pixel data of the actual screen, and then the rest is just the borders and the refresh of the screen, so don't worry about that. So that's the definition, but we actually need to do the dirty work before we can use that definition, and here it is here. So the first thing we do here is we're doing a bit of a speed up on the Enterprise. There's a trick you can do that speeds the Enterprise up a little bit, so we're doing that because we want all the speed we can have. And this actually means the Enterprise is now faster than the Amstrad CPC because it's running at a full 4 megahertz. So now here we're defining the border as black. What we do next is we're using a function called vid, which is a bit tricky. Let's have a look at it. Now, I apologize for the complexity here. I'm going to only cover this very quickly because I'm kind of suggesting you just don't worry too much about it at the moment, but I don't want to not tell you anything about it. So what we're doing is we're getting the end of file, and that's because we need some spare memory. And then what we do is we put a 0 there. We're going to what we have to do is we have to get a memory bank within the first 64K of the Enterprise memory, but the way the Enterprise allocates memory, it starts from the 128K banks first. So we trick the Enterprise into giving us a 64K bank by repeatedly requesting banks until it gives us one. And that's what happens here. So we're using this RST6, which is the Enterprise EXOS function, and we're requesting a segment with a 60K segment with the command 24. We keep doing this until it either fails, in which case it will return, or if it doesn't fail, we check if we've got a bank in the 64K, and if we haven't, we keep requesting them, storing the ones we were given in that spare space at the end of the file. When we finally get one, then we jump to we jump down to here, and what we do is we then go over that memory we just stored all of the unwanted segments in, and we tell the operating system we didn't actually want them at all, you can have them back, and that frees them up for later. And then we return. As I say, I know this is complex, don't understand it, just ignore it. It's not. I'm going to make sure all the code I give you will work and that all of this will work automatically for you, but I don't want to insult you by not telling you this stuff, because heck, if I can figure it out, I'm sure you can as well. And I don't think it's fair to pretend that what's happening isn't what's happening. So as I say, just ignore it if you're confused. I know I'm rushing it. We're going to go over all of this later when we start discussing bank swapping and things. But at this point, I want to just give you the quick basics. So now we've got a bank. Now we've got a bank we can use for the screen. We load it into the accessible memory. We'll cover this in a later lesson again. Now what we need to do next is we need to work out where that is and then set in our line pointer table the address, and then now what we need to do is we need to copy the data we've got here in our program code into that bank that we just got from the system within that first 64K, because the Enterprise's screen hardware can only access a bank in that first 64K. So that's why we're doing all of this hard work here. It's to get that get the data into that area, and then once we've got to here, we tell the graphics system to show the data we've just shown, and we return. Now, I'm sorry, I know that was very complex, but that's really the nature of the beast, shall we say. We're going to go into this more when we do palettes and things, and we'll do screen flipping probably later, and we'll look at it in more detail then. So please, just if that just all went completely over your head, just shrug and say, well, whatever. It is complex, but it's not necessary. So there we go. Well, I hope you found all of this interesting today. It's only a skeleton at the moment. It doesn't really do anything very useful, but if you want to have a play around with it, go ahead. One thing I would say is, while all of the functions I'm showing you today, and I will continue to show you on the other platforms, and when we will extend later, they're all perfectly functional, they're perfectly usable. But if you want to create your own sprite routines and you want to be fast, what I would do is I'd take my code, use it as a template, get your own code based on it working, and then optimize, because you know, things like this command here, caching the thing here, that's going to be wasteful. And things like in this header here, pushing and popping registers to protect them, well, maybe your code doesn't need to protect them. So there's going to be things that my code is doing that is superfluous. And when you're doing screen memory functions, when you're trying to get sprites on screen, every second counts, and every byte of every command counts. So if you can strip a few commands out, just do it. So use this as a template, get your code working, use my hopefully reliable code to get so that you know what you're doing and you know what you're doing is possible, and then just strip it down to the bare essentials to get it to do what you need it to do. And that will give you fast code that hopefully you didn't tear your hair out in the process of doing. Anyway, I hope you've enjoyed today's lesson. We're going to move on next week to some other systems. I haven't quite decided which yet, but we will cover all of the main systems we're doing over the next 3 lessons, the next 2 lessons now, because we've finished this one. I hope you've enjoyed it. Thanks for watching, and goodbye.